Thanks a lot. So my talk today is going to be about Markov decision processes. And I want to talk about some of the practical issues that can arise when we want to implement Markov decision processes in large scale as well as data-driven environments. So let me start by just setting the scene and reminding you of the type of problems that I'm going to look at in my talk. I'm interested in Markov decision processes. That's a predominant paradigm for formulating, analyzing, and solving multi-stage decision problems that are affected by uncertainty. And for the purpose of much of my talk, I will consider Markov decision process to be a tuple SA QPR lambda, where S and A represent the state and action spaces of the system that we want to study. So think of S as the set of all the possible future states of the world that we might find ourselves in, and A as the set of decisions that we can take in any of those states. In my talk, I'll make a strong assumption here. I'll assume that we can finitely enumerate all the possible states that we might find ourselves in, and that we have finitely many decisions that we can choose from. I will assume that all the actions are applicable in any of the states, but that comes without any loss of generality. That's just to simplify the exposition. I will then assume that the initial state of my system can either be known deterministically, or it could itself be random. And in either case, I will describe the initial state through a probability vector Q, the initial state distribution, which has a component for each state of my Markov decision process. And that component denotes the probability with which the corresponding state is the starting state. The most important object in the definition of a Markov decision process is the transition kernel P. And that describes the one-step dynamics of our system. So P, mathematically speaking, is a tensor. It takes as input the current state S and the current action A. And it gives us a probability distribution over the next states. Underlying this notion of a transition kernel is the Markov assumption here, which says that in order to characterize the next state of our system, we only need to know the current state and the current action. The past history of states and actions is irrelevant for that. I then pick up rewards for visiting state action pairs, and I want to maximize the rewards at a discount rate of lambda. So in other words, in this problem, our objective is going to be to find a policy, which is a mapping of states to actions, that maximize the expected total discounted reward. The expected total discounted reward is simply the sum of all the rewards that we get over an infinite but discrete time horizon, discounted at a factor lambda. And if you note, the rewards, they depend on the uncertain states. So these rewards are themselves uncertain quantities. And I want to find a policy pi that maximizes this infinite sum in expectation. Let me have a look at a small example that I will revisit a couple of times later on in the talk. This is the so-called card pole example. It's a standard example in control theory, but it has also been used in reinforcement learning. The idea here is the following. We have a pole that is mounted on top of a card, and we want to balance the pole for as long as possible, only by shifting the card to the left or right. Now, if we look at this problem, this card pole example, through the lenses of a Markov decision process, the most natural way to describe this problem would be through, or the state space of this problem would be through a subset of R4. The state of this problem could be described by a four-dimensional vector, x, theta, x dot, theta dot, where x describes the position of the card on the tracks. And part of the problem is that it's limited to a finite region. Theta is the angle of the pole, and then x dot and theta dot are the first-order derivatives. Now, this definition of the state space would not be compatible with our previous assumption that the states need to be finitely enumerable. So what one does in reality, and that will cause issues, we'll see that later on. In reality, we discretize the state space in order to make it fit the previous definition. All right? The action space in this example is simple. We have two actions. We can shift the card to the left or to the right. The initial state is chosen randomly according to some uniform distributions. The transition kernel here is actually somewhat special in the sense that there is no uncertainty in this problem because the transitions are governed by the laws of mechanics that are known to us. And then finally, we have a unit reward for every time period where we can still balance the pole so as to encourage policies that can balance the pole for as long as possible. Now I have implemented this problem. I discretized the state space into 15 to the power 4 states. I only show you the first two components of the state space here. And I've implemented this MDP. I solved it with a method called value iteration. I'll get back to that method later on. And I wanted to briefly show you this optimal policy in action. So you can see here how the policy tries to balance the pole by shifting the card to the left and to the right. And it does quite a good job at it. It is not perfect because it's limited to controlling the system at a rate of 50 hertz. So there are going to be errors that build up. At some point, the card leaves the feasible region and then the problem starts again. But overall, it does a quite good job at balancing the pole. All right. Those were just some well-known foundations of Markov decision processes. Let me now talk a little bit about some of the more current issues that are being studied in the field. And the first issue that I would like to talk about is the issue of ambiguity. So it turns out that Markov decision processes naturally faithfully model stochasticity through the use of transition kernels, but they do not account for discrepancies of the transition kernel that we use in our model versus the real dynamics out there, which I define as ambiguity. And in my understanding, ambiguity arises from at least two different sources. One, which I will call modeling errors, and another one, which I will call estimation errors. So let's look at those two sources of ambiguity in turn. Modeling errors pretty much always arise when we take a problem from the real world and we try to solve it mathematically on a computer. Because as soon as we do that, we need to make design decisions. We need to decide which effects are first order that we want to capture in our model, and which effects are second order that we decide to ignore because we believe it's not crucial for our model. In the context of our card pole example, we may incur modeling errors by discretizing the state space. Recall that I said that the state space would most naturally be described as a subset of R4. But what I did instead is I discretized the state space into 15 to the power 4 states. Now, when I did so, it turned out that the policy, the optimal policy, was still pretty good. It manages to balance the pole for an average of 32 seconds, which is considered to be a good value in this problem. It turns out, however, that in the same framework, if I discretize the state space into only 10 to the power 4 states, the optimal policy would have performed really poorly. It would have gone down to balancing the pole for about 2.5 seconds per run only. Yes? Thank you.
The real, how are you assessing the performance in the real world, right? Because you have to make assumptions about how your policy is performing.
That's right. Thank you. So what I do have is I have a simulation model, which I take as the ground truth, the real world. That simulation model works at a rate of 50 hertz. So 50 times a second, it would ask the policy, what shall I do? Should I push the card to the left or to the right? And then it simulates based on the systems, the equations that describe this system, where the pole ends up and where the card ends up as a result of that. So that's so I don't have a physical experiment, but I have a simulation model that tells me what is happening there. And that simulation model has a continuous state space, whereas in the MDP, I look at the real world, but then, in the MDP, I have only a discrete state space, right? Whereas in the simulation model, that would not be the case. That's right. The simulation is the ground truth. You're absolutely right. Thank you. So if I were to choose a coarser discretization I begin to realize my Markov decision process is actually very brittle in some sense. The optimal policy heavily depends, in this case, the way I implemented it at least, on the discretization that I choose. A second major source of ambiguity is estimation errors. In this framework of Markov decision processes, we assume that we know the transition kernel that describes these one-step dynamics. In reality, that's typically not the case. This object, the transition kernel, has to be estimated from data. And whenever we estimate objects from data, we normally incur an estimation error. And we know that estimation errors tend to get amplified if we use the output of an estimation as an input to optimization. Now, in the card pole example, I don't suffer from estimation errors because we assumed we know the laws of mechanics. But I could try to simulate a source of estimation error through a distribution shift where I assume that I learn my policy in a wind-still environment, but I afterwards implement it in a slightly windy environment where there's a stochastic amount of wind that can blow either to the left or to the right, and that adds to the action that I apply to the card. And again, it turns out that if I were to do so, the performance of my optimal policy in the Markov decision process would deteriorate quite dramatically. Now, those sources of ambiguity are quite well understood in the optimization literature. And one of the main approaches in optimization to dealing with ambiguity is robust optimization. And applied to the concept of Markov decision processes, we would be talking about robust Markov decision processes. So this is one approach with which we can potentially alleviate the negative impact of ambiguity. And I will show you in those two examples of modeling and estimation errors in a moment how robust optimization can help. Now, in a robust MDP, we again want to find a policy that maximizes the expected total discounted reward. But now we assume that the one-step dynamics that are given through the transition kernel P, they are not known exactly, but we only know that they belong to some ambiguity set script P. And we play a game against an adversarial nature where we need to find a policy pi that performs best in view of the worst transition kernel from within this set script P, the so-called ambiguity set. And now, let me show you the same two examples again. Recall the first example was the issue of modeling errors, where now we discretize not into 15 to the power 4 states, but 10 to the power 4 states. And let me show you the optimal nominal policy and the optimal robust policy on the same problem instances. So the problem data is the same. And as you can see, the nominal policy performs very poorly. The robust policy will not perform as well as under the fine state space discretization, but it does perform quite a bit better than the nominal policy. In fact, instead of managing to balance the pole for 2.5 seconds on average, it manages to balance the pole for about 15 seconds. Not close to the 32 seconds under the fine discretization, but it does manage to alleviate some of the negative impacts of modeling errors. And the same holds true for estimation errors. Here, in both cases, we have the nominal policy up top and the robust policy at the bottom. We see here a blue bar that is the random wind speed that we apply. And we can again see that on the same problem instances, the robust policy does a better job at balancing this pole. All right. So going back briefly to this slide, so far, the purpose of my talk has been to try to convince you that when we want to implement Markov decision processes, ambiguity is probably an issue that we should be concerned about. And robust optimization, and in this case, robust Markov decision processes, are one approach to alleviate the negative impact of ambiguity. Not the only approach, but one of them. Now, assuming we are buying into this reasoning, there are at least two questions that we would need to answer. The first one is, how should we choose an ambiguity set P? Because ideally, we don't just want to choose it heuristically, but we want to have some kind of principled approach to choosing P. And secondly, how do we actually find an optimal policy for this problem? because it's quite well understood how we find optimal policies for a traditional non-robust Markov decision process, but this is a different problem here. All right, so let me try to address those two questions in order. The first one is the construction of an ambiguity set. And let me on this slide just give you a high-level overview first of my approach, and then I will elaborate on the next slides. What I will do is, let me just check whether the chat questions are current or, sorry, that was just a sound. All right, in order to construct the ambiguity set, I will start with what I call a structural ambiguity set. That is going to encapsulate all the information that I have about this transition kernel P without yet resorting to any statistics. I will then intersect the structural ambiguity set with a data-driven ambiguity set that I will derive from a historical sample of the Markov decision process. And then I will end up, the intersection will give me some out-of-sample performance guarantees, some guarantees of how well the MDP will be doing under the unknown true transition kernel. All right, let's look at those two steps in turn. The structural ambiguity set, as I mentioned, should capture all the a priori information that we have about the transition kernel. And I will make the assumption here that the unknown true kernel lies in the relative interior of that set. What that means in practice is I need to know which transitions happen with probability 1 and which transitions happen with probability 0. That will be needed for the statistics later on. In the simplest case, that's all that we know. We have an MDP, we say, well, some transitions I know they happen with probability 1, whereas others, they can be anything between 0 and 1. I might have more information. For example, if you think about a typical example of Markov decision processes, a typical application is predictive maintenance. You might not know the rate at which your machines deteriorate, but you might know that this rate is uniform over time. That would be the case where you may not know the deterioration rate psi, but you know that for different transitions, the unknown transition probability would be the same. Encapsulating this information in an a priori set helps us to reduce the number of parameters that we need to estimate, and hence it makes our statistics platform better. All right, now to the data-driven part of constructing this ambiguity set. The setting that I will look at here is somewhat similar to off-policy learning in reinforcement learning. What I assume is that we have access to a state action history that was generated by some historical policy pi0. Not the optimal policy. It could be the optimal policy, it could be any policy. But we know the policy, and we have observed the transitions that the Markov decision process did under this policy in the past. And what I would like to do is I would like to use this state action history to reason about the transition kernel P. Now, if we were to give this problem to a statistician, quite possibly the first idea that comes to mind is to look at the maximum likelihood estimator. The maximum likelihood estimator is based on the likelihood function, which tells us for a given transition kernel P, how likely is it to observe this state action history under P. And the maximum likelihood estimator is then simply the transition kernel P under which the observed state action history has the highest likelihood. Now, the maximum likelihood estimator would give us a point estimate for the transition kernel. But what we want is an ambiguity set of potential transition kernels. So what we will do is we look at our ambiguity set, we choose, oh dear, I pressed the wrong button. Sorry. Okay. As our ambiguity set, what we will choose is we will choose all the transition kernels P whose log likelihood is almost as large as the log likelihood of the maximum likelihood estimator, modulo some constant delta that we need to choose. If we choose delta small, we essentially only have the maximum likelihood estimator. If we choose delta large, we have many more transition kernels. So how should we choose delta? Let us assume that the historical policy that generated this state action history is sufficiently diversified so that it visits every state infinitely often if the state action history would grow infinitely long. Under this assumption, I propose to choose this constant delta from the previous slide as the 1 minus beta quantile of a chi-square distribution with a number kappa of degrees of freedom that we can specify what it is, that we can characterize. And with this choice, one can show that the unknown true transition kernel will lie in our ambiguity set with probability exactly 1 minus beta as the length of the observation history goes large. So in other words, we can give ourselves a beta, and then with a confidence of 1 minus beta, the unknown true transition kernel will actually be in our ambiguity set. And that gives us an out-of-sample performance guarantee in the sense that, recall, our policy performs best in view of the worst transition kernel within the ambiguity set. Now we know that the true transition kernel is in the ambiguity set with a probability of 1 minus beta. So that means with probability 1 minus beta, we will be positively surprised when we implement our policy in the real world, because we have hedged for the same transition kernel or perhaps even a worse one. But of course, this property could potentially come at a price of an unreasonably large ambiguity set. So in order to understand this, let's make the following stronger assumption. We can relax this assumption, but for the purposes of this talk, I would like to keep it like this. Imagine the historical policy was so diversified that if the observation history would become infinitely long, we would visit each state action pair infinitely often. In that case, one can show that our ambiguity set converges in Hausdorff distance to a singleton set that only contains the unknown true transition kernel. And this convergence happens at the standard statistical rate of 1 over square root n. So in other words, what we have in practice is we have some observation history. We might have 300 observations of the Markov decision process, maybe 400, maybe 500. Whichever, no matter how many observations we have, the unknown true transition kernel is going to be contained with probability at least 1 minus beta. And the longer the historical observation is, the smaller our ambiguity set is. It kind of gets sucked into this singleton set with the unknown true transition kernel. All right. From a statistical viewpoint, I believe the ambiguity set that I was just presenting is meaningful, but that's only one side of the story. Of course, we also need an ambiguity set that we can compute things on, that we can compute an optimal policy for. And unfortunately, it turns out that in general, for the class of ambiguity sets that I was just discussing, we can generate instances where all the optimal policies are randomized as well as history dependent. What that means is, in order to get an optimal policy, the policy needs to remember all the past states and actions that we have visited. And that is impractical because we're looking at infinite horizon problems, so we would need infinite amounts of memory. Also, one can show that the Bellman optimality principle over those general ambiguity sets is violated, and in fact, just computing the expected total discounted reward of a fixed memoryless policy is strongly NP-hard. So because of that, people have already, starting from the 70s, looked at special classes of ambiguity sets with properties that bring them closer to traditional non-robust Markov decision processes. And by far the most popular class of such ambiguity sets is the class of SA rectangular ambiguity sets. So the idea here is that our ambiguity set is actually the cross product of many smaller ambiguity sets, one for each state action pair. Under this assumption, one can show that there is always an optimal policy that is memoryless and deterministic, and the Bellman optimality principle continues to hold. So in essence, all the nice properties from traditional non-robust Markov decision processes carry over to robust Markov decision processes over SA rectangular ambiguity sets. Unfortunately, SA rectangular ambiguity sets can be very conservative. Let me show you the following example to illustrate this. Imagine we have a very simple toy Markov decision process with 3 states. We deterministically start in state 1, and we either end up in state 2, where we receive a reward, or in state 3, where we do not receive any rewards. And we can influence our luck by choosing either action 1, which is the left action, or action 2, which is the right action. The problem is we don't know the transition probabilities to the nice state. It is psi under action 1 and 1 minus psi under action 2, but psi can take any value between 0 and 1. It turns out that the best we can do in this example is to randomize equally between both actions. Because then it doesn't matter which value psi nature chooses, we will end up in the desirable state 2 with probability 1/2. However, under the assumption of SA rectangularity, we give nature more power. Instead of choosing a single value of psi, nature would be able to choose 2 different values, psi1 and psi2, that can both range between 0 and 1. That's what SA rectangularity would imply in that example. And as a result, under SA rectangularity, nature would simply set psi1 to 0 and psi2 to 1. And then under no policy would we ever reach state 2. So because of this, people have looked at wider classes of ambiguity sets for which we can still perform tractable computations. And one such class is the class of S-rectangular ambiguity sets, where we again assume that the ambiguity set is a cross product of smaller sets. However, now just one set for each state as opposed to one set for each state action pair. It turns out that under S-rectangular ambiguity sets, the optimal policy is guaranteed to be history independent, but it might be randomized. Perhaps more importantly, the Bellman optimality principle continues to hold, so there's hope that we can actually perform reasonably efficient computations under S-rectangular robust MDPs. Actually, if we get back to this example, it turns out that this is an example of an S-rectangular robust MDP. So under S-rectangularity, we would indeed find the optimal policy here, which is the randomized policy. All right. So this is a partial answer to the first question. What kind of ambiguity set should we choose? What I would now want to do is I want to turn a bit to computing optimal policies. And to this end, I will focus on S-rectangular ambiguity sets. I will focus on S-rectangular ambiguity sets. Now, let us recall how we typically obtain optimal policies in traditional non-robust Markov decision processes. We normally obtain them through the Bellman optimality equations. This is a system of nonlinear equations. The unknowns here are the V stars of S. So we have one such equation for each state of the Markov decision process. And V star of S denotes the expected total discounted reward that we can expect to get if we start the Markov decision process in state S and we implement the optimal policy throughout. And this optimal reward to go is equal to the one-step rewards that we get when we're in state S plus the expected future reward to go discounted by one time period. That's lambda, and we take the best possible action in order to get the optimal policy. That's the Bellman optimality equations. Those are the equations that we normally solve in non-robust MDPs to get an optimal policy. And it turns out that under S-rectangularity, we can get an optimal policy by solving a very similar set of equations. I call them robust Bellman equations here. The equations look essentially exactly as before, only 2 key differences. First of all, we now choose the worst transition kernel from within the set PS, because we don't know the transition kernel exactly. And secondly, we don't choose just the maximum over all deterministic actions, but we're allowed to randomize between actions. So that's the set of optimality equations that we need to solve. We then get a worst case optimal reward to go function, and then it's easy to get the optimal policy once we have that function. How can we solve those nonlinear equations? Well, it turns out that if we interpret the right-hand side as an operator that takes as input an estimate of our optimal value to go function, and that spits out a refined estimate, if we see this as an operator, then this operator is actually a contraction mapping. And the Banach fixed point theorem guarantees us that if we apply this contraction mapping on any initial estimate of our value to go function sufficiently many times, we converge to the optimal value to go function at a geometric rate, because that's the fixed point of those optimality equations. Okay, so what that means in practice is for S-rectangular robust MDPs, we need to solve this max-min problem many, many times. We need to solve it once for each state of the Markov decision process in order to complete one iteration of this solution process. And we typically need to run it for several hundred iterations to get to a solution that is close to optimal. So this problem needs to be solved hundreds of thousands of times, if not millions of times. In principle, we can use classic ideas from robust optimization. We can dualize this minimization problem. We get a single stage problem that under the suitable assumptions can be solved in polynomial time using primal dual interior point methods. But in reality, that would be way too slow. It would take way too much time to do that. So what we do instead is we look at a specific class of ambiguity sets, PS, for which hopefully we can do those computations much more efficiently. And a class of ambiguity sets that we propose here is, you can think of them as balls in the space of probability distributions. You have some kind of best guess that could be the maximum likelihood estimator or any other transition kernel. And you want to look at all the transition kernels that are sufficiently close with respect to some phi divergence d. It's literally some distance function in the space of discrete probability distributions. I will consider specific choices of d later on. For now, I just assume it is some distance function. All right. So let's look at how we can solve this problem efficiently. The first thing we can observe is that this objective function here is bi-affine in pi and p. And those two feasible regions here are convex. So I can apply a minimax theorem to exchange the order of the maximum and the minimum operators. Now I can observe that we are supposed to take our actions, our randomized actions, after observing the transition kernel. But then we're back in the non-robust setting, so we can actually take actions deterministically. We no longer have to randomize. You can see this. We are maximizing here a linear function of pi over the probability simplex. There will always be a maximum that is attained at an extreme point of the probability simplex, which are the deterministically executed actions. So this is the problem that I need to solve. It's still not clear to me how I can solve it efficiently. So what I will do is I will use a bisection search. I will probe logarithmically many candidate objective values theta and ask myself, is the optimal value of this min-max problem less than or equal to theta or not? All right, let's plug in now our definition of the ambiguity set PS. It was this set of, ball centered at the empirical distribution. And now if we look at this problem here, this min-max problem, then from a high-level perspective, what we're asking ourselves is there a p for which f of p is less than or equal to theta, while g of p is less than or equal to kappa? But we can turn the argument around. I can equally ask myself, is there a P for which G of P is less than or equal to kappa, while F of P is less than or equal to theta? May not be obvious why I would want to turn this around, but if we look at the resulting problem, this problem now completely decomposes along the actions. We have as feasible region the A-fold probability, the A-fold cross product of the probability simplex. The objective function is linearly separable in our actions, and we have a separate constraint for each action. So this problem is actually equal to the sum of A smaller problems that only operate over a single probability simplex, as opposed to an A-fold cross product of probability simplices. And this resulting problem actually has a very intuitive interpretation. This resulting problem here, this inner minimization problem, I think of it as a generalized projection. It asks us to project the center of our ambiguity set P0 onto the intersection of a probability simplex and one linear inequality constraint. And the projection happens with respect to whichever divergence we choose. Now, this is now a very well-structured problem, and we can think about very efficient methods to solve this for different divergences. So let me summarize. For the class of distance-constrained ambiguity sets, we have observed that computing the robust Bellman operator can be reduced to solving a sequence of those generalized projection problems. In other words, if we can solve those problems efficiently, there's hope that we can solve this problem efficiently. This can be made formal. If the projection problem can be solved in time h of s, then the Bellman operator can be solved in time a times s times h of s times a log error, where a is the number of actions and s the number of states. We have implemented such algorithms for a number of different divergences. So we looked at the Kullback-Leibler divergence, the Burg entropy, and the 1 and 2 norm distances. And for each of them, we developed efficient algorithms to solve the projection problem, which gave then rise to efficient algorithms to computing the robust Bellman operator. And here are the runtimes of our algorithms. I ignore, for lack of space, the log error term. And on the right, we compare it against the previous state of the art, the fastest algorithms that have been proposed in the literature for those divergences over the Bellman operator. And what we can see is that for several divergences, we get better runtime estimates than the previously best known algorithms, whereas for others, we get algorithms quite easily where no previous algorithms have been known. If you look at those runtimes, by the way, you can see that computing the Bellman operator for a non-robust MDP would take time OS squared times A, because we need to go through every state, we need to look at every action, and then we need to compute an expectation over S follow-up states. So in other words, we get a complexity of S squared times A already if there's no robustness present in the Markov decision process. Now, for those phi divergences, the only thing that we add is a logarithmic factor. So that tells us that at least in terms of complexity theory, we must either be optimal or close to optimal, because we only add a logarithmic factor on top of what is a clear lower bound for our problem. We have implemented this. Let me see how I do time-wise. We have implemented this on synthetically generated test instances and the Kullback-Leibler divergence. And what we see here is, as a function of the problem size, that's the number of states in the MDP, the runtimes of MOSEC, which is a commercial solver in blue, and our runtimes in red. On the left for the projection problem, on the right for the robust Bellman operator. Now, these dotted lines give us the speed up of our algorithm, and you can see that for the projection subproblem, we're about 250 times faster than MOSEC. Whereas for computing the robust Bellman operator, the speed up increases, and already for an MDP with 300 states, we are about 1,200 times faster with a very naive implementation. So it really helps to exploit problem structure here. All right, I have a few more minutes left. I want to briefly touch about a different topic, and that is how can we scale Markov decision processes to large problems? This is typically nowadays done through approximations of the value function, such as in approximate dynamic programming or reinforcement learning. But I want to show that in some cases, we can also exploit problem structure to scale to larger problems. And this part of our research was the question was brought to me by colleagues from the School of Public Health, and they were interested in studying patient prioritization. So it turns out that in England, ever since the outbreak of the COVID pandemic, the number of people that are waiting for treatment in hospital has skyrocketed from about 4.5 million people in 2020 to now about 8 million people in 2024. What that means is in England, we simply cannot treat all the people that are waiting for hospital treatment in a hospital in time. That is not possible, so we have to prioritize given the limited resources that we have. And then difficult questions arise. Who should we choose first? Which disease group should we prefer over other disease groups? Should we prefer younger people over older people? Should we prefer frail people over otherwise healthy people? And should those priorities change between summer, when it's relatively calm in English hospitals, over the winter when we fight the annual flu outbreak? So we decided to study this problem from the perspective of Markov decision processes. And in particular, what we did is we modeled each of those waiting patients as a Markov decision process. The MDP that we used had 15 states and 6 actions. I give you a high-level overview of a smaller version of that MDP here. The main idea is the following. Here, the pictures represent patient states. The arcs represent stochastic transitions, and the arc labels represent actions that lead to those transitions. So broadly, in our model, we assume that a patient first waits for treatment. He or she is then admitted to hospital, either as a scheduled appointment or as an emergency appointment. For example, if we keep postponing a procedure for too long. The patient is then treated either in general and acute care or critical care or a combination thereof, and will stay in hospital for a stochastic amount of time. And then finally, the patient is released from hospital, hopefully healthy and well, but of course, this is not always the case. So what my colleagues from the School of Public Health did is they estimated those transition probabilities for 3,300 different patient groups. Based on real-life data, it was a mix of publicly available health data in the UK, as well as we have Imperial College has some hospitals where we could use COVID data from, because that was not publicly available at that time. Okay, so now that we have a Markov decision process for every patient, we can put all those patient-level MDPs into one single large Markov decision process. The state and action spaces of this large Markov decision process emerge from the cross products of the patient-wise MDP state and action spaces. So you can think of the state of this large Markov decision process as a 10 million dimensional vector, where each component records the state of one of our patients. And likewise, each action is 10 million dimensional because we have an action for each patient that we need to select. We can then determine the dynamics and the reward structure of the Markov decision process from the individual patient level quantities. The rewards, by the way, are here years of life gained, as well as potentially healthcare costs avoided. And we now look at a problem over a finite time horizon. We normally look at 1.5 years of weekly time periods. What binds those different patient MDPs together is the competition for the same resources. We model in our in our model of the UK healthcare system as resources, junior doctors, senior doctors, nurses, and different types of hospital beds. Those were the resources that my colleagues identified as most critical in the English healthcare system. Okay, so our goal is going to be, again, to find a policy that maximizes the expected total reward, however, now over a finite time horizon and without discounting. Now, if you look at this MDP, it has about 15 to the power 10 million states and 6 to the power 10 million actions. So clearly, this MDP will not be solvable by itself. What we do is we apply a fluid approximation to this MDP. So you can think of this intuitively as we assume that we could arbitrarily split each patient into pieces, treat those pieces independently from each other, and then those pieces evolve independently through the system. If we do so, it turns out that the solution to this relaxed MDP becomes equivalent to the solution of a linear program. I won't go through the details here of this linear program, but basically it has two sets of decision variables: sigma, which roughly records the states, and pi, which records our policy. In particular, sigma ti of si records in week t for patient I what percentage of that patient is in state si. And likewise, the policy records for week t and patient I what percentage of the patient is in state si, and we apply action AI to. And then what we try to do is we try to maximize the expected total rewards over all time periods, patients, and state action pairs for each patient, subject to constraints on the initial patient population, the one-step dynamics of the patients, the resource constraints, and we have a constraint that no patients get lost at the end of the week. This linear program scales linearly in the number of patients. And since we group patients into different groups, we don't treat every patient individually, but we have 3,300 different patient groups based on age, frailty, and disease type. It becomes a linear program with about 200,000-300,000 decision variables that we can solve in about 1 to 2 minutes. Now, it's quite easy to show that this linear program gives us an upper bound on what we could achieve in the optimal policy for the original MDP. But this linear program also allows us to recover a randomized policy for the original MDP. That randomized policy is fairly standard. What we do is we interpret the continuous decision variables in our linear program as the probability with which we take certain actions in the real MDP. And one can show that if we do that, this policy, this randomized policy, actually enjoys a quite strong performance guarantee. If we suitably adapt our resource availabilities, we have the formula for that in the paper, what we need to do. Then the randomized policy will be feasible with very high probability, going to 1 very quickly as the system gets large. And the relative suboptimality, so the percentage suboptimality, goes to 0 as the number of patients increases. So I have yes, please.
Theory of weakly coupled MDPs, there's these Lagrangian methods you can use also. Did you think about trying those?
Absolutely, it's a good point. So it turns out it was quite embarrassing. We didn't know about the Lagrangian methods. It turns out that the explanation that I gave you in order to how we got the fluid LP is the same as just a standard Lagrangian relaxation. So that part, the fluid LP part, this here is basically standard theory in weakly coupled MDPs. Now, what was non-standard was this performance guarantee, because the only other performance guarantee that we found in the literature for weakly coupled MDPs with this level of generality had a an optimality gap that was exponential in the time periods, in the number of time periods. There was a paper from Brown and Zhang in 2021, I believe, Management Science. And they got a performance bound that was scaling 2 to the power t. And that would have been difficult in our case because we look normally at 1.5 years time horizon at a weekly horizon. So we have t equal to, I don't know, something like 80 or something. So that bound didn't seem suitable for us. Yes.
The cost or reward summation overall agents.
Yeah.
Here the optimality gaps. Do you have to do sort of normalization in order to if your cost n goes to infinity, the original cost will just go to.
Oh yeah. Thank you. That's why I'm talking about so two things here. It's the relative gap, right? Not the absolute gap. So I'm talking about the reward generated by the optimal policy, the reward generated by the optimal policy divided by the reward generated by us minus 1. But then also remember that the number of states and actions for each individual patient is fixed. It's 15 and 6. So the rewards are naturally bounded already because it's a finite set. Thank you. Yeah. Yes?
I actually wondering if you could speak more about the structure. Like what exactly is it mathematically?
Yeah, absolutely. So in this case, right, we're looking again at a finite state, and for each individual patient, we're looking at a finite state and action space. So the reward, you can think of it just as a vector, right? Or as it's a function of S that can vary from 1 to Si and A that varies from 1 to AI. Now we had long discussions with the School of Public Health as well as our health economists. What would be a good reward function to use? Ultimately, we decided to use mostly years of life gained over some baseline policy to apply. It amazed me, and to correct me if you have better understanding of them, but it turns out to be quite a sensitive topic in healthcare to think about what's your objective function, because that's not how people, how surgeons or something would think. They think about, we try to help everyone, and we're not trying to prioritize one life over another life. But that is certainly so. I think the two criteria that are most accepted are probably mortality. So how many deaths can you avoid? Or years of life gained, which is a bit more fine-grained, which assumes that assuming you would not be treated versus I treat you now, how many lives have you gained extra? The key difference between the two is that years of life gained probably will prefer younger patients because they have potentially more life remaining. Oh yeah, I'm running out of time. Let me just tell you briefly. We applied this to what happened during the COVID period in England to our best understanding. So one of the co-authors on that paper was actually one of the key advisors to the UK government, and still we were not quite sure what happened. But this is our best understanding. You can see here, during the summer months, England was able to treat some patients electively in 2020. Over the winter months, there was a large number of patients that wanted to go to A&E, accidents and emergency, and that were just sent away, either to field hospitals or sent home. And this is what our policy would have done. You might not necessarily see a huge difference here, but it turns out that quite a lot of things are different. Now, this is a very high level. We have a policy paper on that where we have a much more detailed analysis. But broadly, what our policy would have done under the assumptions of our model, of course, is it would have treated more, it would have treated less COVID patients to the benefit of some other disease groups that have been let's say, radically undertreated in England in 2020. And under the assumptions of our model, which is of course not what reality would mean, but this change in policy could have had a significant impact. And we have two papers on this. One of them is in Nature Computational Science. There we have lots of different possible scenarios that our healthcare colleagues came up with. And it seemed that in a broad range of scenarios, such an optimized schedule would have indeed performed better than the one implemented by the UK government. That brings me to the end of my talk. Thanks a lot for coming, and thanks for all your questions. Thank you.
So because of time, we can ask questions offline. Thank you so much.
Thank you. Thank you. Thanks, Adrian.